gentlemen. Provost, thank you very much for the invitation to be here and also for your very warm introduction. I'm very happy to be here this afternoon. I know that we're running late through no fault of ours. We can blame it on the traffic coming out of Porter's Lane. So I probably will skip over some of these slides and we can have a discussion further on. But I also wanted to thank your colleague, Dean, who is here. She was very instrumental in arranging for me to be here this afternoon and for the visit today. You can see that she spent a part of her work last summer with us in Canada at one of our research sites. Came out and visited some of the irrigation work that we were doing out in the field and also in our lab. So Nadine is also the connection as to why I'm here this afternoon as well. So thank you. Now, just to give the presentation into a bit of a broader context, I wanted to talk a little bit about the situation that we're in today with respect to the global food crisis. And to put this into perspective, you'll see that we have had a very successful food production system globally, extremely successful. If you look at the area harvested, it has remained relatively constant over the past 40 to 50 years. But although that area has remained relatively constant, you will see that yields of our major cereals have increased dramatically over the last 40 to 45 years. Production then has therefore increased dramatically. And you'll notice that this all originated in the 1960s, 1970s, and in the 1980s. This was a lot due to the Green Revolution. So that the impact of the Green Revolution in terms of new germplasm, new genetic material varieties, and also fertilizer and other chemical inputs has helped in a large part with this, but genetics being a very major part in terms of new germplasm and crop breeding programs. So we've had a very successful Green Revolution. One can also challenge the Green Revolution. One can say that not all of the benefits were equally distributed. Yes, that is safe to assume. And one can challenge what have been some of the environmental, socioeconomic benefits of the Green Revolution, but one cannot challenge the fact that when we had large masses of people on the Indian subcontinent, India, Pakistan, Bangladesh, just around the time when Bangladesh was formed in the early 70s, and also in parts of Africa, the Green Revolution, and parts of Latin America, the Green Revolution did play a role in helping to address hunger, malnutrition, starvation, and death. So that we can't fault at all about the Green Revolution, despite some of the shortcomings. Now, I just put this on to show you afterwards that we've seen the same thing continuing on up until virtually today with respect to major crops, and also in the livestock industry. So there has been quite a massive improvement in agricultural production worldwide, a lot of it being in Asia, in Latin America, some parts of Africa. However, despite all of these successes that we've witnessed in the last 40 to 50 years, we still have unprecedented rising hunger and malnutrition, as evidenced here by parts of the Horn of Africa and also in Asia. And where do we see this the most? Well, you'll notice that the number of people who suffer from hunger and malnutrition is roughly about 1 billion people, probably gone down a little bit over the past few years, since 2010, 2011, probably dropped a little bit. But if we look back at the promises that were made at the World Food Summit to halve the number of people who suffer from hunger and malnutrition from about 800 million to about 400 million by the year 2015, we are anywhere near that number Instead, we have seen an increase in the number of people who suffer from hunger and malnutrition. So this is a cause of concern. Where do most of those billion people or so live? Well, just around half are in Asia and Pacific, and not hard to imagine when you consider that the two most populous countries of India and China are comprised in that red area where we have our large population masses. You see Latin America and the Caribbean is relatively small, but sub-Saharan Africa is the second largest area affected by hunger and malnutrition. So that gives you an idea of where efforts need to be focused in going forward. Now, the FAO predicts that we would have to double food production over the next 25 years to meet the demands for food for a growing population, which is expected to reach 9 billion people by the year 2050, plus the number of people who are affected by hunger and malnutrition right now of close to 800 million, 900 million or so. And also the fact that in many of our emerging economies, we see, for example, India and China today with rising affluence, that the movement away from traditional diets to more energy, high-protein diets with large amounts of meat, all of these are changing the food demands and food requirements, and we need to think about that as we go forward. So what are some of the major drivers around this food crisis that we need to be concerned about today? Well, first of all, the whole aspect of climatic variability, impacts of floods and droughts, competition of water from other sectors of the economy, agriculture, which I'll show you before, traditionally uses globally about 70% of the fresh water that is withdrawn globally. That number is shrinking, that percentage is shrinking because of the fact that we have rising demands for water from municipalities, urban development, industrial development, and now we have to pay attention to environmental in-stream flows, and that competition for water is going to drive the whole sector, irrigation sector, water production, further into efficiency and conservation. Population growth, I just talked about that as well. The demands for energy and alternative fuels, I want to come back to that as we talk about the water, food, energy nexus, because of the whole biofuels situation, and elaborate on that a bit. I talked about the dietary pattern changes that we see as a result of economic growth in China, India, and other emerging economies, particularly in Eastern Europe, former Eastern Europe, and environmental, land and water quality, degradation, which is putting a pressure on the amount of land and water available for agriculture and food production. And as we witnessed back in 2008, one of the factors that was brought out very clearly by the donor community, the international organizations such as IFAD and the World Bank, FAO, was that countries were not invested in their agricultural sector. And I presume Trinidad is probably no different to that. It's only now we start to see reinvestments in agriculture and food security, and we've seen that this decline in investment in agriculture and food production has been one of the reasons why we haven't got the technical expertise and the capacity to deal with some of the food production problems that emerged during the food crisis, as well as the fact that we haven't been invested money in research and technology transfer and support to farmers. That has all declined, and even now we're trying to rebuild this at a global level, and we don't have enough human resources capacity available to do the turnaround, as well. I'm pleased that at places like UTT, this subject of water and food production and so on is being taken seriously to help to address the situation. The demand for food, as you can see here, is going to be very significant in the emerging countries. I want to emphasize that because you'll see that in the developed countries, the population is remaining relatively constant. And one of the things that we sometimes think is that this number is actually larger than it really is, the least developed countries. And so we think that we have to put a tremendous amount of effort, or most of the effort, in food production should go in these developed countries? Well, of course, yes, we must put effort. But in terms of food production, meeting the demands for food, it's going to be these emerging countries that we see here, some of them in South America and Southeast Asia, places like Vietnam, Cambodia, Thailand, and Eastern Europe, where a lot of effort is going to have to be placed in terms of food, meeting the food needs of those areas. Now, the problem that we're looking at today is very much compounded around this whole issue of price volatility, fluctuations in prices of food commodities and also energy. And the two are very closely linked. And you'll see here how food prices vary. This is the FAO food price index. So this is an index, this is not dollars. So indexed to 100. And these are average food prices for an average food basket. You'll see here 2008, when we had the food crisis first emerging with the green line, and then food prices dropped down. And then you'll see in 2009, started to come back up. 2010, food prices went up even higher. 2011, quite high. And 2012 started to flatten off a bit. So there really has been quite a bit of volatility in food prices. And one can look back and see what are some of the reasons. And there are probably as many reasons as there are people in this room. But we know that one of the biggest factors that drove these prices has been weather in the major grain-producing countries of the world. Forest fires in Russia, droughts in the Midwest United States, floods in the Midwest United States, floods in Canada, and the same thing in Europe. So, forest fires, floods, droughts, these all play a very major role in terms of the changes in the prices. There's also speculation, where people on the stock market use food as we do with oil and other commodities, and this became an important factor as well in terms of speculation. Using food in the stock market to speculate on prices also had an impact. And we've talked about some of the other drivers already with respect to water shortages, water scarcity, lack of investments, and so on. Now, here is what has happened with energy prices right up until 2012, going back to 1998, 99, and you'll see how, thank you very much. You can see how prices in dollars, for example, the red line is in euros, but if we stay with the blue line, prices in dollars, you can see how prices have varied. And oil prices, they're coming down towards the end of 2008, started to climb back up in 2009, and fluctuated quite a bit there in 2012. Now, the linkage between here and here is very clear, because energy is a major input to the production of food. When we talk about fertilizers, for example, you well know that since you have fertilizer plants here. The byproducts from the petroleum industry go into food production. You depend on energy to move products in and out, moving inputs into the field, taking processed commodities out from the field, or raw commodities out from the field. You then go into processing plants, for example, to convert raw materials into processed food products. You need energy, and then you use transportation to take those products to the consumer, to the market, to the consumer. So a very strong linkage between food prices and energy prices. So this whole relationship between food and energy, one cannot ignore it. And this whole volatility between the prices, nothing remaining constant with time, puts uncertainty into the market, puts uncertainty into investments in agriculture as well, and makes the planning for people who are involved in planning of production of food for export and local consumption quite difficult, because we're not being able to predict carefully and clearly when prices fluctuate the way they are. So I want to come back to this whole issue of biofuels as well, because it has an impact on what we're talking about. And as you know, the US, under former President Bush, had created this energy security plan before he left office and before President Obama came into power. And I'll show you a graph right after this where you can see the impacts of that energy security plan in terms of the capacity that went into the production of ethanol and the construction of these ethanol plants. And when we had the crisis, the food crisis in 2008, May 2008, this whole question about using food-producing lands to produce fuel became a moral and an ethical debate and dilemma, as you can see here. And so we put subsidies into ethanol production, or countries put subsidies into ethanol production, capacity went up for ethanol production, and we took prime agricultural lands out of food production into ethanol production. And so when you go back to those price volatility graphs that I showed you, this also had a major impact on the fluctuations in those graphs, because you were now not able to depend reliably on those lands, major tracts of land, particularly in places like Mexico and China for food production, because it went into fuel production. So this also was a very grave problem that one had to face. Now here is the ethanol capacity and production in the United States. And you'll notice here first this purple dotted line, which shows you the expansion plans that went into place in the United States. And you'll see here in 2007, 2008, when President Bush presented his energy security plan, this is where the corn lobby and the politicians, then together with the private sector, put significant amounts of money into investments in biofuel production facilities and ethanol plants. And then you'll notice here that it's started to taper down. And we don't see all those big planning capacity programs anymore for ethanol in the United States. But what you will notice here is how the production in billions of gallons per year has been climbing, and then in about 2011, 2012, it's remained pretty much flat, and it's estimated that for 2013, it's actually going to drop a little bit. So this whole climb that you see here, the plan for production facilities, had a major impact on those prices that we saw in the price volatility graph. And now, as things flatten off, one wonders, well, what's going to happen in the future? And coupled with this factor is also the other factor that other things are being used as feedstock for biofuel production, non-food producing materials. People are talking about algae, for example, waste from the pulp and paper industry, waste from restaurants and supermarkets and so on, going into biofuel production. If that takes off and becomes a conversion efficiency becomes larger and better, more improved, then maybe this reliance on corn as the feedstock might change. Just to quickly show, this was the effects of drought last year. I think many of you are familiar with this. In the Midwest United States, large grain-producing region that puts large volumes of corn, soybeans, wheat into the international cereal reserves affected by significant droughts last year. So let me focus a little bit on the water issue now. And we are looking at a situation of increasing water scarcity, the need to combat drought, water stress, and the impacts of climate change on the future with respect to food production. Well, I'm not going to spend much time on this because I think most of you are familiar, but this is from the Stern review that was done in 2008, and you'll see what some of the impacts could be, which are well known, but here you'll see falling yields in many developed regions, higher temperatures, as a result, increased temperatures causing that decline in yields simply because of the crops that we have today are not able to withstand 2, 3, 4 degree increases in temperature. And it's estimated when you look at models, some of these climate models, regional and global climate models, that we will see a shift in the area that is covered by the semi-arid tropics could probably increase by about 11% there, particularly in the semi-arid tropics of Asia and Africa. And when you consider that the semi-arid tropics is the home to about 800 million people, this is in Burkina Faso, where I was a couple of years ago on a DFAT project, and we were out in here in Decagon, and you can see the effects of drought and feedstock for animals and the very parched areas there, unbelievable in terms of being able to get a crop out of those places. And this is another well-known map that came out of the International Water Management Institute that looked at the areas that will be affected by water scarcity, both physical water scarcity and economic water scarcity, in terms of people not being able to afford to buy or purchase water. You'll see large parts of Africa. Here it's a bit different because you're in equatorial Africa, in the Great Lakes region, where there's a lot more water. The Middle East, large parts of India, Central Asia, China, and parts of Central America, South America. You'll also see what are the impacts with respect to the areas that will be impacted by water scarcity. Now, to put this into a global perspective, we have about 1,500 million hectares of cropland worldwide. And out of this 1,500 million hectares, roughly, we say 20% of that area is irrigated. So roughly about 300 million hectares of that global cropland area is irrigated. What is very interesting to note here is that this 20% of cropland produces 40% of the world's food. So we cannot ignore the benefits and importance of irrigation in terms of the world food production, which then means that the difference is what is left for rain-fed production, and 60% of the world's food comes from that rain-fed land. However, the problem is, big difference between these two regions is that here you can maintain, if your irrigation system is working properly, you can maintain a stable yield. Here, you're very much dependent on rainfall. So the yield coming off of this area is not as stable as the yield coming off here, and you're limited sometimes to just one crop a year from these areas. Here you can get 2 to 3 crops a year, depending on what type of crop. So this is one of the importances of that 40%, is that you are able to maintain a stable yield base, which you cannot do from rain-fed lands. Simply to show you where most of that irrigated land is, not a miracle number, 70% of it, roughly about 200 million hectares, is in Asia. So India, China, Southeast Asia, Philippines, Indonesia, Malaysia, Thailand, Vietnam. Those are your major irrigated countries, 70%. And you'll see here, for example, North Central America, only about 10%, South America, 4%. So irrigation, relatively small in these parts. Where it's biggest is in Asia. I mentioned to you that irrigation worldwide on a global basis uses about 70% of the fresh water that is withdrawn. And that's on a global basis. Of course, places like Trinidad, Ghana will use a lot less, and North America, Europe, a lot less. But the big irrigated countries, and there's some that are using even more than that, 90% have done a lot of work in Egypt. 90%, 92% of Egypt's fresh water from the Nile goes into irrigation. So there's some countries which are even higher. The same thing in the 5 Central Asian republics, from the Amu Darya River, the Sir Darya River, which drain into the Aral Sea, then they're using 80-something percent, 85, 86, 88% of their fresh water goes into irrigation. And how much longer can this happen when we see here that the manufacturing sector, industrial development, domestic, urban development, and so on are all rising, and if we put, in addition to that, the amount of water that is being consumed or ought to be consumed by the environment for environmental in-stream flows, then agriculture cannot rely on its traditional 70% in the future. However, when you look at the projections of the food that is being required, you'll see here for the year 2050, if we said we're going to double food production, then the amount of water that's going to have to go in, as you'll notice here from where we are today, is also quite significant. Not quite half, or double, but get fairly close to the amount of water. And where will we find that water from? It's not only competition from other sectors, but it is also, as I said, because of climate change. So what are some of the solutions that we're talking about? Well, obviously, we have to look at the increases in land and water productivity, and how can we increase biomass, productive biomass per unit area of land and per unit input of water per liter or per cubic meter of water to be able to increase productivity. And some of it will be done through genetic improvement, again, as we saw before, so that quite a bit, particularly in the private sector, a lot of this research is being done by Pioneer, Monsanto, DuPont, the big seed companies, to be able to breed species that are more drought tolerant, can save water. And on the engineering side of things, certainly we need to do more in terms of rehabilitation and maintenance, improvement of our infrastructure. That can help quite significantly as well. And the point that I want to focus on this afternoon, because it is some of the work that Nadine has started with us, is in this whole area of water savings technologies. And I believe that this is one area which is very ripe for exploitation that we have not done as much on as we have done in terms of main irrigation structures, canal systems, and so on. So what are we talking about in terms of these technologies? We're talking about a range of technologies that span the continuum of water supply from dams, through canals, right through to the field levels and beyond into the soil. And this is where we were in the onion field that you were asking about. So this is Australia, where I had a chance to spend some time on a sabbatical leave looking at what they have been doing. I was actually quite involved with them on my sabbatical leave, helping with some of this work that was done in the state of Victoria, particularly northern Victoria, where new gates, new radial controlled gates were designed, and these controlled gates are very much a different type of thinking, introduced a different level of thinking than one had imagined before. Because right now, or before the introduction of these systems, we had very much a supply-driven irrigation system. The dams were filled with water during the rainy season. During the dry season, you lower the gates, you let the water out. The farmers would take water as and when needed, and whatever they didn't use continued on downstream, flooded, polluted, wasted whatever, percolated down into the groundwater, caused the groundwater table to rise. So this system moves from a supply-driven system to a demand-driven system. And if you want to look at what has been one of the most successful case studies in terms of water conservation, this is one of the best case studies to look at in terms of what has happened in northern Victoria, in the breadbasket of the state of Victoria, and they call it, this was a $1 billion Australian dollar project where a major Australian company was involved in the development of this. All of this technology was developed locally in Australia. So the way it works is that the irrigation districts and the farmers in the irrigation districts had to, first of all, pay for water. Water was no longer free. And that was because this followed, all of these developments followed 10 years of drought in Australia and tremendous water shortages. So, first of all, they had to pay for water. Secondly, they had to have a duty, a water duty or a water right to take so much water based on the area that could be irrigated, safely irrigated, without causing groundwater pollution problems, salinity problems, and so on. And then once that volume of water was established, these gates were regulated back by this panel to a control station in the office of the irrigation district. So knowing the water duty, the controller would then, from his or her computer, be able to relay signals to regulate these gates to release only the amount of water that was required by the growers. So moving away from a very much a supply-driven irrigation system to a demand-driven irrigation system, all with electronic controls. And the company that has developed this has done extremely well. Rubicon is the name of the company. I had a chance to spend some time with them in Melbourne, and at the University of Melbourne in their hydraulics laboratories, where these gates were built, and they have now done a remarkable job, as I said, for $1 billion to convert all the old dams and control structures now to these new Rubicon gates with telemetry controls and water pricing mechanisms. So that's going at the upstream end. Going downstream end into the field, things like drip irrigation, some work we did in Central Asia in trying to better design furrows and regulate the amount of water going into the furrows to reduce seepage, water losses, percolation, and so on. And some work which Nadine saw with us that we're doing, where we're measuring in the soil, trying to control what's going on in the soil, which I'll elaborate on some more, with sensors, capacitance probes, frequency probes. We're trying to accurately measure soil moisture. We're measuring rainfall, wind speed, temperature, relative humidity, and trying to match the amount of water we put into the soil based on constant monitoring of rainfall, all climatic factors, and crop growth. And so trying to match these two things and not leaving it to the farmer to decide how much water to put on, when to put on, but going to much more scientific controls to the point now where this is the kind of thing you could train the system through all kinds of artificial intelligence controls now to take this on. So managing this soil water reservoir, knowing what the evapotranspiration is, knowing the precipitation, you can calculate the irrigation. So really trying to learn a lot more in this yellow box is where I have been focusing a lot of my efforts. So, as I said, what we did is that we had students would go out into the field and would measure. We went to Leamington, I think, with Felix. So this was in Leamington, and two of our summer students here who are collecting soil samples in the field with an auger, so a farmer could test with his hands, her hands, when to irrigate, or you can take soil samples, weigh them, get the weight of the soil, and determine when to irrigate. Well, as you can imagine, this is very time-consuming. So some of the things that we have been working on is these probes that one can leave now in the field for in situ measurements, and through either data loggers, or here you can see this particular probe has a, can send a wireless signal by antenna back to a base station. We can actually measure at all kinds of depths. So you put this capacitance probe down into the field, 1 meter, 1.5 meters down. You could, at every one of them, you can adjust these rings to whatever depth you want. So every 25 centimeters, every 30 centimeters, we could know exactly. Up in the root zone, we can put them even closer in the active root zone. So we can actually look at water extraction patterns within the root zone as well. But by even going deeper, we can tell whether water is leaking or seeping or percolating down out of the root zone rather than being taken up by the crop. So these are some of the things that we're very excited about. And this is one that I promised to help Nadine with. For her work here, and we're using this in some other projects we're doing in the Caribbean, where we're measuring with these frequency domain probes in the soil. And again, you can get these probes to any depth you want. We've been using them in the 0 to 30 centimeter zone, the active rooted zone of the crop. We can measure immediately what the soil moisture is. We can also connect this up to a data logger and have it remotely collected. But to be able to use those probes, we need to have one of these calibration curves. This is the same case where we just developed this curve for some plot work we're doing out there. And you'll see that you get some values here from the probe itself that have to be converted to volumetric water content. So what we did, these points here, every time we took a reading with those Decagon probes, we measured the gravimetric soil moisture content. We converted the gravimetric soil moisture content to a bulk density, to a volumetric moisture content to the bulk density, and we were able to plot these points. And then you can see we used here, for example, a linear relationship, what the R squared is. We could get a slightly better improvement if we use the quadratic or the linear relationship. We can get almost an R squared of 0.9. But one of the things about this graph is that you need several points along here from field capacity going down to wilting point to be able to have the most accurate prediction. And the whole goal of this is from work from one of my PhD students who just finished, whom Nadine worked with and visited his work in the field, is that we can set these lower limits of soil moisture, upper limits of soil moisture, and then using those probes, we can decide when to turn the irrigation system on, when to turn it off. So as you can see here, moisture content is dropping, going down to the lower limit. We turn the system back on and bring the moisture content back up to the upper limit, which can be close to field capacity. And you get this sawtooth curve as you turn the system on, turn it off. That's how it behaves on a daily basis. But really, this is what you're trying to do. And here you can see now the water content. This is down in the month of October. So we've stopped irrigating, the crop goes into senescence. And so we allow the soil to dry out because there's no need for water anymore. But this is what we're trying to do with irrigation scheduling on a real-time basis using those probes. And the good thing about it is that now we can do this on a regional basis. So instead of just working at one field, we can take several fields. And it doesn't matter how many fields, there's no limitation to the number of fields, it's all data. And so the only limitation you have is the bandwidth, that's all. And these are small number. This is very small compared to what you have on your iPhone or your BlackBerry. Certainly not the same number of data points. So if your BlackBerry and your iPhone can work and you're transmitting much more data, this is a piece of cake to take all these data points from our different field locations, send it into a central processor, and have all of that on a computer. And then based on that information, those curves you saw, I can then send this information back out now into the field to trigger those sensors on and off. So I measure stuff, bring it in, process it, I send it back out, and I can control the system for hundreds of farmers. This is not rocket science. It can be done. So, some of the work that we're doing, and I'm going to show you an example in Ghana, because it's a very interesting example, is this model that we built, which is a very simple model, actually. Just looking at the water balance of what goes on in the soil profile. We have all the inputs into the profile, being the rain and irrigation. This is the controlling depth of the soil, which we're using as the root zone, maybe a bit deeper than the root zone. Any water that goes outside the root zone is lost as percolation. Any that runs off the surface is lost as surface runoff. And of course, a major component during the dry season is the irrigation, is the evapotranspiration. Right? That's your major driving force. So the big thing is to be able to get a very good handle on two things to make this model work. The two things we need are the evapotranspiration and to know what the soil properties are in terms of field capacity, in terms of wilting point, in terms of the moisture holding status. And this is tricky, as I will show you from the example we're doing in Ghana. So if we just rewrite this equation, then the amount of irrigation water we need is the crop evapotranspiration, plus the runoff, plus the percolation, plus or minus the change in soil water storage from yesterday to today, minus whatever rainfall occurred, right? The rainfall from it, which is very critical in wet areas, okay? Because the rainfall is part. That's why we have supplemental irrigation. So this here has quite a bit to it. And I know as you drive around, you see evaporation pans, right, Professor? Professor Ekwe is an expert in these evaporation pans. So we can measure from evaporation pans what the evapotranspiration from a pan is. Now, how do you convert the evaporation from a pan to a crop? Well, of course, we have pan factors, and then we have crop consumptive use coefficients. But if you look at these pan factors, Kp, and you look at the crop consumptive use coefficients, Kc, these are all factors that were developed in the US, right? Places like Texas and Idaho and so on. They don't pertain to our conditions. So one of the biggest challenges we have, and this is an area that needs a lot further work, is how to get pan factors that are relevant to the region that you can convert from pan evaporation to a crop evapotranspiration. So we could use that, we have used that in our model, but we decided to do something a little bit more sophisticated. We went to this FAO Penman-Monteith equation because it's based on an energy balance. And as I showed you from the little met station that we had or on the ground, we can measure the radiation, solar radiation, we can measure the temperature, we can measure the wind speed. So we know everything here, psychrometric constants and so on, saturated vapor pressure. All of this data is available from the NOAA website where they're monitoring a lot of this data globally. So the temperatures, of course, we need, and wind speed we need to measure on the site. And then we can get what we call the potential evapotranspiration, ETO. Now the potential evapotranspiration is the rate at which the plant will transpire if water is not a limiting factor in the root zone. But since water is a limiting factor in the root zone, we then need to convert the reference evapotranspiration to a crop ET. So as I was saying, and these are the kinds of things that Professor Ekwe works on, we can take the potential evapotranspiration, we can multiply it by the crop consumptive coefficient, and we can get what the ET for the crop is. So the big question is, how good are these values of Kc? So we have been doing some global literature work on this, different soil types, different moisture levels, and coming up with some of these kinds of graphs for beans, cabbage, and so on, tomatoes, as to what the values of Kc could be, and reading off these values here right up until 100% when the crop canopy is fully developed, when the plant is transpiring at maximum rate, to be able to get our crop ET, which we then put into that equation to run the water balance. But this is a very tricky part now when we come to the soil. And it's not as easy as one might think. So here's in Guyana, where we do some work right now. We take these cores, soil cores, we bring them back to our lab in our faculty, and I think we were working with these. So I've seen how our field assistants all were working with these. So we put these cores in here, and on this pressure plate, which has a ceramic membrane in here, connect up to our pressure cylinder, we can subject. First of all, we saturate up these cores, leave them in a bucket of water, let them become fully saturated, and then we put them in here and we start to apply our pressure to them, draw the water out, and then we can measure at different pressures how much is the water drawn out to be able to plot what we call the soil water retention curves. So this is for an area on the Quarantine coast of Guyana that we just actually brought the samples back, had them run recently, and this is one of the challenges that you would find. First of all, if you look here at the percentage of clay, and you'll see very high percentages of clay, 36% clay, 34% clay. You'll have the same things when you run your samples here. These clay samples cause a lot of problems for us. They're much more difficult to work with than the silty soils and the sandy soils. Because the first thing you'll notice here, we took a lot of sites. We have 1, 2, 3 sites. We actually have more than that. And we have at different depths, 0 to 15, 15 to 30, 30 to 45 centimeters. You will see the scatter on those graphs from those different sites at different depths. So the question is then, what do you take as your water retention curve when you have all of this scatter? Okay. This becomes now a geostatistical problem. How do you do things like kriging, independent component analysis with your samples to be able to get average curves for each depth? So this is not a very easy thing. And you look at these, there's a big difference between this red line and this blue line in terms of water content. So depending on which curve you take, you could be under-irrigated or over-irrigated. Okay? So this is not a trivial matter. And I'm sure, Professor Ekwe, you've had to deal with this, I know, in your own work. This is a very complicated situation if you're going to start to estimate irrigation requirements. So, to give you an example then, we took different sites here, 0 to 15, 15 to 30, 30 to 45, and then we took the average between 0 and 30, 0 to 45. And I just want to show you here, as I zoom it up for these graphs, how much at a third of a bar at field capacity, look, between two, how big a difference you can get between the field capacity water content. It is almost on a heavy clay. That difference is almost equal to the amount of water that's stored in the soil between field capacity and, let's say, 75 or 50% of field capacity that you want to irrigate to. So this is not a trivial matter, very complicated matter. Okay, so we took that graph, did the best we could. As I said, we did some kriging, geostatistical analysis. We got some data. And then I looked back. I had some data from one of the sugar estates near to our field site from 1956 to 2010. You can see the long-term historical time series there with the rainfall. And Guyana has this very pronounced short dry season in here, a longer dry season in here from September to October. And last year, 2012, have a look at the rainfalls that they experienced there. Last year, the rainfalls were higher than the historical level. And I also have some other graph that I didn't, for sake of time, show to you, is that ever since what they call in Ghana the mother of all floods in 2005, this whole pattern has changed. You look at every single year, the rainfalls have been dramatically higher than the long-term historical average. So when people talk about climate change, and they talk it's going to get hotter, it's going to get drier, well, maybe in some parts that might happen, but I'm not sure in Ghana. It seems to be the other way around. It's going to get wetter if we just, but mind you, it's just short. Between 2005 and 2012, in the broad scheme of things, only 7 years of data. Who knows? I know again, Professor Stone and Professor Eckwood work on all these rainfall records, and they have probably a lot more information on this than I have. So I put all that rainfall data for 2012, July to December, into that soil water model, and with the ET and everything else, percolation, and so you'll see here what's going on with the dynamics of the water. We did this on a daily basis, then we summed it up on a monthly basis, and you have the rainfalls here in blue, each of the months. You have the evapotranspiration that we calculated from the FAO Penland-Monteith method. And then I have the amount of surface runoff. And what is interesting is that for this dry season, which I showed you, this historical long dry season, which we have here from August until December, it's not so dry because, as you can see, we're getting these rainfalls. But that's not the only thing. As you can see, we're also getting runoff during that so-called dry season. And what is also interesting is that we're also getting now, when we run the water balance model, some deficits. And for each of the months, the largest deficit being here in September. So I looked at this September data a bit closer, and here I have the September data for you, because I wanted to understand a bit more of this situation with the surplus and the deficit, so you can see on a daily basis what the deficits are. Okay, so what I should be doing, this is my lower limit. I want to irrigate up to here, and what I should be doing is then bringing the water up. The funny thing, when you look at this graph, and I don't know if you've figured it out as yet, is that every time I have this deficit problem here shown by the red lines, the thing that you'll notice here is that we have these very high soil moisture levels. So, you know, when you start to think about how you're going to plan for this, it becomes a challenge. Because when you add everything up, my surplus is 680, my deficit is 303 millimeters. So this is one of the challenges we have when we talk about plan for irrigation. These things work a lot nicer, or could work a lot nicer, and we have no surplus, no percolation. We just have a deficit, and all we're doing is trying to meet the deficit. And we're doing right now, we planted crops, vegetable crops, for this experiment. We're showing no difference in yield between irrigated and non-irrigated, simply because we're getting these large surpluses which are counteracting the deficits. Now, you're very hot and dry here, I notice today. I don't know what's going to happen tomorrow, what happened yesterday, but hopefully, if you run it, you might have more luck than I have, because you wouldn't have this, hopefully, this big deficit that I'm finding in our so-called dry season. So the dry season is not as dry as we used to think. So let me close now from one challenge to another challenge, and this is something that we call site-specific or river rate irrigation technology, because it makes use of all the things I've shown you with sensors and the models to be able, and I did this with a center pivot system, but it's true for any system, drip, sprinkler, but it just shows better here. Here you have the pivot arm going around, and the whole goal here is to break the area covered by the irrigated section into what we call different management zones. And so we don't put the same amount of water on here as we do here. Each one of these has a different water application rate. And if we can now manage water through this site-specific or variable rate technology, we would even go further in terms of water savings, water use efficiency. And so this is where we spend a lot of time. I have a graduate student, Jan Argy, who's working with me on this, how to create these management zones. So we're taking some maps of soil type, elevation, electrical conductivity from irrigated areas in Alberta on the center pivot. And we're taking each of these zones here in 2-degree arcs. And we're taking 2 degrees, 4 degrees, 6 degrees, 8 degrees. And we're trying to see, using, again, geostatistics and crop yield models, what's the advantage? If I go to a 2-degree arc, I have many more management zones. And could you imagine what that's going to do for me in terms of regulating the speed at which this arm goes and also the pressure to the nozzles and the application rate from the nozzle? It's going to make life very complicated using BID controllers and so on. So the question is, instead of 2-degree arcs, if I was to go to 4, 8, because I have to go in multiples of 2, so 2, 4, 8, 16, 32-degree arcs, I get fewer zones, and now I even measure yield, which my graduate student is doing, and we can also use crop models to predict the yield under the zones. I want to know how far can I go with those arcs, because the less management zones without compromising yield makes the job a lot easier in terms of the hardware. So the only thing that I can vary is the speed at which that boom is moving and the pressure to each of these nozzles, hence the application rate from each of those nozzles to meet the water required for each control zone. So this, I think, has a lot of potential, and here is one of the areas that we're working on. And what I want to show you is just outside of Lethbridge, Alberta. Have a look at any one of these areas covered by a pivot. And the first thing you'll notice is how variable, which you don't see when you're a farmer right there on the spot, but these maps, this thing is a for instance. So, you look at here how variable it is, okay? And you can see where elevation, salt, you can see the white areas where the salt is accumulating from salinity, and the impact that that is having on crop yield. And that's what we're trying to overcome. How can we get more of these uniform circles, therefore uniform yield, by managing the pivot according to elevation, soil type, salinity, and so on. And this, to me, is an amazing thing if we can get it to work. And we can apply this to whatever, to drip systems, sprinkler systems. I think it's amazing. So I think I'm going to stop at this point, and I'll be happy to